And now, without further ado, I'm happy to announce the first of our guest talks. This talk is titled Towards More Carbon Efficient Federated Learning, and it's going to be given by Philipp Wiesner. I hope I pronounced that properly, who is a research associate at EU Berlin. So Philipp, the floor is yours. Please go ahead. I'll stop sharing my screen.
Cool, great. Yeah, thanks for the introduction. So I'm Philipp, and I'm doing research on carbon efficient computing systems, and since about 2 years with a focus on federated learning. And let me maybe kick off this talk by explaining what carbon efficiency means in the sense of computing. So in carbon efficient computing, or carbon aware computing, it's also called, we're trying to align the power consumption of a computing system, in this case now a federated learning system, with the availability of clean energy. And as you know, like the biggest sources of renewable energy that we currently deploy are solar and wind, and they are highly variable. So we basically try to consume energy where and when the sun is shining, for example. So we are trying to exploit these spatio-temporal patterns that arise from these energy sources. And in this work particularly, we are focusing on something that is called renewable excess energy, also called curtailed energy or stranded energy. And this always occurs if in a certain area of the grid, we have more supply than demand at a certain time. And this is actually occurring more and more often as we're deploying more and more renewables, because in the past, we only had variability on the consumption side, but we were able to fully control our power production. And now, additionally, we have uncertainty and variability in the production side. So we're a bit losing control. And these areas, these periods of times are becoming more and more frequent. And actually, they're highly problematic, because what are we doing with this excess energy? The most straightforward idea, of course, would be to store it. So we basically transfer it through time to use it at a later point in time. Now, the problem with energy storage is that it's really expensive, and it's always only available in limited capacity. So it doesn't really make sense to buy 100 or 1,000 of batteries if they're just idle 90% of the year, just to accommodate some peak loads. Additionally, we have conversion losses, we have increased battery aging with frequent charge cycles, and so on and so forth. So energy storage, it makes sense, and it's important, and it's able to mitigate the problem to a certain degree, but it's not really solving the problem. The second option that we have is transferring excess energy to neighboring regions. So we're basically transferring it through space. And here we have similar constraints. Also, grid capacity is limited. We're seeing this frequently in Germany, where we have a lot of very big offshore wind parks in the north of the country, but all the consumers, all the big industry is in the south or the west. And the grid in Germany is currently not strong enough to transfer all this energy to these regions. And additionally, excess energy patterns often correlate in neighboring regions because they have similar weather, for example. Now, if none of these two options is available, then the only thing we can do is curtail the energy. That means we waste the energy. We don't even produce it, or we transfer it into heat or something like this. Sounds stupid, but it's actually a common practice. So in 2022, the California system operator had to curtail around 7% of their entire solar power production. And Germany, as I said, curtails a lot of its offshore wind energy, and China had to curtail 15% of their entire renewable energy production that year. And here on the right, you can see that this problem is getting worse and worse as we are deploying more and more renewables. So one of the most important solutions is that also the energy consumers need to become more flexible. They need to consume less when no energy is available, and they need to consume more once the energy is available. And we're now applying this basically to data centers, and particularly to federated learning. Because turns out that federated learning is a really good use case and a very interesting use case for this. Because not only we have a very energy intensive task, it's also spanning over time. So we have like this time axis to schedule on, and also it's geographically distributed, often even globally distributed. So we also have this axis. And today I'm presenting at Zero, which we will present at ACME Energy later this year, which is a federated learning system that tries to leverage this energy. So it's a FL system that operates exclusively on renewable excess energy, as well as spare computing capacity at clients. And this is also a very important requirement, because if you would need to buy new hardware to make this work, that would also not be very carbon efficient. And what we're basically doing is client selection. So we're trying to compute, again, when and where energy is clean. But of course, it's not that simple to just always select the cleanest clients. We have several challenges here. The first and most obvious challenge is, of course, we have a very volatile and a highly variable environment. So clients can appear and disappear at any time. They might not be available for longer periods of times if there's no excess energy. So how can we guarantee a fast and efficient training in these environments? The second problem is that we might have common power budgets between clients. So in FedZero, we are mostly considering cross-silo federated learning for the reason that in cross-silo FL, we have usually quite big, powerful, and also power-hungry clients. So a single client can be an entire GPU cluster that consumes hundreds or thousands of watts. And here it really makes sense to address the scheduling problem, because in cross-device federated learning, clients, like individual clients, don't consume a lot. And if we now assume that, for example, we have some excess energy in the UK, it's maybe not the most relevant mitigation strategy to turn on 50 iPhones in that region. So this is why we're focusing on cross-silo FL. But here in cross-silo FL, clients are often co-located. They can be co-located in the same data center, in the same region, and then they often share the same power source or same power purchase agreement. I will talk about that later in a second. The third problem, and that's the most challenging one, is fairness. It's, of course, a big topic in general in machine learning and in federated learning as well. But here it's even worse, because we introduce a lot of unfairness if we bias our client selection strategies to select green clients. And some clients might have a lot more energy available than others. So we really need to take care that we are not introducing biases towards these clients. And lastly, of course, we want a system that is not only scalable, but also robust to forecasting errors, because we're doing our entire client selection strategy based on forecasts of free capacity at clients, as well as renewable excess energy. So we need to handle the problem that maybe at runtime we have vastly different conditions than we expected. And turns out that this all boils down to a big trade-off between final model performance, the convergence speed, and carbon efficiency. So usually we're optimizing for the upper two. We want, of course, well-performing models. And during training, we want fast convergence. And now if we also introduce this carbon efficiency point, we need to sacrifice on at least one of the two. And FedZero does not sacrifice on the model performance, but we sacrifice on convergence speed. So under certain conditions, maybe we need to slow down the training, or maybe even pause the training for some hours to wait until some clients that we consider valuable become available again. I'll now give you a quick overview. I don't want to dive too deep into the approach, but I give you a quick overview about the protocol and the system architecture of FedZero. So in FedZero, as I quickly mentioned before, clients can be co-located under the same power domain. A power domain can actually be a power source. Could be that your data center has some solar panel on its roof, for example, and multiple clients feast from this common energy source. But could also be that this is maybe a power purchase agreement. So you're basically promising some big wind park that you're like buying a certain amount of energy at a certain time and a certain location, and you're powering multiple data centers with this energy. So still multiple clients fight for the same energy source. Now, at the beginning of each training, clients need to provide certain information to the server, which is their computing power, their energy efficiency, and also which power domain they belong to. And after the server gathered all this information, the first round can start, and the server queries forecasts. It queries forecasts for spare capacity at clients. So we do load forecasting at clients to identify when in the future we might have underutilized hardware. And as well, we're querying forecasts for renewable excess energy. So this is mostly based on weather forecasts then in most cases. And after all these forecasts are collected, we can run our optimization problem. which I'm not going to explain in detail. But what we're doing is we're cherry picking clients that have a high system and statistical utility. These two metrics are very, very common in client selection approaches. So we want fast training rounds and we want valuable training rounds. And also, as I said before, we want to take care of fairness. This is also commonly done in client selection. And now here, additionally, we also need to take care of this co-location problem. So since excess energy is a limited resource, we generally want to spread our client selection across many power domains, because if you would select all of these 3 clients, they all have to run on the same limited resource, they might slow down the training and we have slower rounds. So this is our client selection. So now we select a certain subset of participants and tell them to start training. And this is where it gets really interesting. This is a topic that we also continue researching on. At runtime, of course, we might have very different conditions than when we forecasted. There might be more energy, more capacity, less capacity at clients. So they continuously need to communicate with some controller that then adjusts the pace and maybe tells a client to slow down a bit, consume a bit less energy, or tells it to speed up. Because in the end, we have the overall goal that all clients finish roughly at the same time. So we avoid stragglers and have fast and efficient rounds and really utilize the infrastructure and the energy that we have available. And the rest is common procedure. We aggregate all the results. The aggregation strategy is none of Federated business. You can use whatever you like. And we start the next round with very new set of forecasts. Now, as I said, I do not want to go into detail about the client selection or the fairness mitigation or something. But since this is a Flower monthly, I would rather want to talk about how we implemented this in Flower, because this was actually quite challenging. So our evaluation is based on real solar data and real solar forecasts that were provided by Solcast. That's a big solar data provider, as well as load traces based on the Alibaba GPU cluster data set. It's also a very commonly used data set for systems evaluations. And for Fed0 to show effect, we need long trainings. We need really to train over the course of many days. So we execute our trainings over 2 weeks. And now you can maybe already see the problem. Because for our final experiments, just for the final table in our paper, basically, we had 2 energy scenarios. One where all the power domains are co-located. It's 10 cities in Germany. So also all the excess energy patterns are very correlated. And in the second scenario, we have a globally distributed setting. Now we have 2 scenarios. We evaluated 8 approaches or different parameterizations of approaches on 4 different model dataset combinations. And for each experiment, we are doing 5 runs. So this, just for the final table, results in 320 runs. And at least in my lab, we don't have 320 GPUs available, nor do I have years of time. So we needed to come up with a solution to evaluate this a bit more efficiently, because this does not only even cover like the entire experimentation phase, ablation studies, other experiments we did. So what we did in the end, we do perform actual federated learning trainings, but we're simulating the environment and we're simulating time. And we did this by implementing a custom server in Flower that allows discrete event simulation over time series datasets, about time series traces, like, for example, these load traces. And this enables us to do experiments faster than in real time. And also very important, it enables us to skip over periods where no training is performed. So here on the right, you can see in this co-located scenario between 8 in the evening and 4 in the morning, there's no energy available ever because it's night. So we can just skip over those 8 hours. We don't really need to wait. And we implemented the server in a way that at the beginning, it performs, at the beginning of each round, it performs the client selection. So we have a 1-minute step size in our discrete event simulation. And for every 5th minute, we have an entirely new set of forecasts that we previously crawled from Solcast for the next couple of hours. So it performs the selection. It then simulates the real-time behavior of our training rounds. So now we're using like the real traces and not the forecasted ones. And what comes out of this is basically the amount of mini batches that each client would have computed during the next training round. And then we communicate this number to the clients and use the normal Flower simulation utility to execute the training. So this works well. And I would say the first part and the third part are also sound. But to be honest, I think the second part is a bit of the weak spot of our evaluation in this paper. Because it's really hard to simulate real-time behavior unless you execute the real-time system. It's really hard to say what happens when a client has to communicate to the controller has to take a decision, there's communication delays, maybe not everything works out as we planned. So this is only an approximation, of course, how the system would behave in reality. So this entire part here is only simulated so far. Of course, I wouldn't put that big of a focus on it if we weren't working on the solution, because now since about a year, we're working on a co-simulation framework, and now I'm moving on basically to ongoing and future work. It's called WESM. It's a big testbed for carbon-aware applications and systems, so it's for computing systems that have to interact with the energy system. And what WESM is we basically took a bunch of already existing domain-specific simulators, so that's simulators for power production, so solar power production, wind power production, as well as battery simulators, grid simulators, and we plugged them all together in a big co-simulation framework called Mosaic. And what Mosaic does is it takes care that the simulators run in the same pace and that they're also able to exchange messages during runtime. And we basically plugged all of these simulators together and built a nice interface around it. And then now what you can do in this example now for federated learning, your federated learning clients, no matter if they are real clients like real devices or simulated devices, they would periodically communicate their power usage to a microgrid simulation, and you can have multiple of those in parallel. And then WESM takes care of simulating basically what the energy system would do by also in parallel running power production simulators and so on. And then you as a user are able to implement controllers. And a simple controller, for example, could be a monitor, which just periodically writes down the state of the energy system to your disk or shows it in a graphical user interface or something. But you're also able to implement an API server, like some REST server, that gives visibility and control to your computing system at real time. So this is called software-in-the-loop simulation. So while your training is running, your federated learning client can actually query this API and ask, okay, how much energy do we have available? What are forecasts? What is the state of my simulated battery? And so on. And from the point of view of the federated learning client, this is supposed to behave like a real energy system. And it's, of course, highly scalable because it's all simulated. I think this will open up a lot of very interesting new research directions if you really go into a bit more depth of how federated learning systems can interact with their energy system. And we currently have a lot of ongoing research projects that try to make this a bit more usable in Flower and maybe come up with some nice interfaces between FL systems and energy systems. We're also trying to make some evaluations how well these simulations perform compared to real hardware test beds, and so on and so forth. And with this, I'm already coming to an end. So I presented FedZero, which is a federated learning system that exclusively runs on renewable excess energy and spare computing capacity. And what we're currently working, and FedZero here, it's the code is open source. You can look at it on GitHub. It's all implemented based on Flower. And WESM is this co-simulator that I just talked about. You can also try it out already. We have some documentation, and the API is pretty stable by now. As I said, we're working on it since a year or more. But of course, a lot of stuff will improve. WESM also comes with all the data sets that we used in the evaluation for FedZero. It comes also with some more data sets on carbon intensity that were provided by WattTime. And give it a try and feel free to reach out to us. And thanks for your attention.
Okay, well, I think this was an amazing talk. I have from Slack a couple of questions.
Mm-hmm.
And if the rest of the audience in the meantime can think about some questions if you feel like asking something. So the first question I have is related to when you were talking about FedZero, you were describing 3 steps you follow to run a huge experiment. And you were saying that the second one was the most complex one. So the question is the output of part 2 like a series of configurations that your strategy would send to its client, like, configure fit in Flower in the strategies? Is this the output of part of the step 2 here? For the client to receive it and know, I need to, because I'm in a peak of a lot of excess, I can train for 1,000 batches instead of 10 batches.
Exactly. Yeah, it's like that. So the simulation is also an optimization problem. It gets as an input basically the expected amount of work that the first step comes up with. So the first step says, okay, I'm expecting this and that client to compute 60 mini batches during the next round. But it's doing that based on forecasts. And now in the second step, we're like approximating how the system would behave now if we have the real traces. And with the real traces, now we of course know maybe there was less capacity available than we thought. So now out of this comes, no, it's not 60 batches that we managed, it's only 40. And then those 40 would be exactly communicated using configure fit to the clients, who's then executing the training.
Okay. So then this means that when there was no excess, like those, like for example, from 20 hours to 24 hours, clients will get like basically train for 0 batches, so you will exit immediately, speed up. So the round.
We wouldn't even notify, we wouldn't even start the simulation engine.
Okay, yeah.
It would just loop over it until there's actually training to be performed. And then, but we do need the training to be performed because we need the output of the training for the next client selection round. So in our case, we need the local losses because we use them to approximate the statistical utility of clients.
The second question I have here is about testing. So the question is, does it make sense to connect so you were talking about this monitor controller.
Mm-hmm.
Does it make sense? Would it make more sense to connect it to the strategy so it can then build the configure fit accordingly, or does it make sense to connect it instead to the clients?
Yeah, it's a very good question, and one that I do not yet have an answer to. That's exactly what we're currently also trying to investigate. I think there's probably different settings. Might also be a privacy issue. Maybe the server does not have access to all the energy system information. So the clients have to communicate with their own energy system and only give some more high-level infos like I'm available, I'm not available. I guess it depends on the setting, and this is what I mean. I think there's a lot of interesting research questions that pop out of this. But yeah, I don't know yet.
Okay, cool. Well, cool. Okay, I think those are the questions I see. I have one question on my own, which is, of course, has to be related to baselines. Do you think that Fit 0 could be a Flower baseline?
Could be, but
Or do you think, is it right? Well, you have already open sourced it, I believe.
The code is open source. Yeah, you can look at it. DOS/Fit0.
Mm-hmm.
The thing is that we have this custom server that makes it maybe quite hard to implement it. So it really relies on this custom server that does the discrete event simulation, and the server basically keeps track internally of the time, but it's not easily integrated as a baseline, I guess.
Maybe I can take a look, and if we think there is an opportunity, we can discuss.
Yeah, absolutely.
Okay, great. I think these are all the questions. I don't see questions here on Zoom, so I think this is everything. I think this was super interesting talk, and also quite interesting to see how, depending on like the fairness issue related to the energy source you get. So that was something I was not expecting to see, but it's real. So super cool.
Thanks a lot.